Hello! In this video, I'd like to talk about quantifier elimination for Presburger arithmetic, specifically the natural numbers with just addition. This structure in and of itself does not have quantifier elimination. There are properties that we can express in the first order logic of this structure that we need quantifiers in order to express. That is, we can't express them in a quantifier-free way. In other words, we can't eliminate those quantifiers over this language. So the question becomes, what do we need to add to our language in order to give it quantifier elimination? Our goal is to add just enough that we have quantifier elimination without, of course we can't add in new expressiveness to the language. We want to just add in things to this structure that we could talk about already in the first order logic. We just needed quantifiers in order to talk about those things. And we want to add them in as primitives that we don't need quantifiers for. And the goal is to add in just enough that we get quantifier elimination without adding in so much that it becomes difficult to analyze the expressiveness of the language. The first thing that I'm going to want to add into this language are constants for 0 and 1. If we want to write out some property involving the number 1 without actually using the constant, we can. We can describe it in this structure. There's a formula that describes the number 1, and so we simply need to say that there exists an x which satisfies that formula and fits into the place of 1 within the formula that we're actually trying to express. But of course, this requires a quantifier. In order to be able to get rid of those quantifiers, it would be useful to have 0 and 1 added into our language. I'm going to keep track of what we want to add into our language on the side of the board. Of course, we could add in constant symbols for every element of the natural numbers, but we really don't need to for our purposes here. If we want to talk about the number 2, we can just write it as 1 plus 1, and that's perfectly fine. We don't need quantifiers to do that. I'm just going to use numbers as shorthand for 1 added to itself that many times. Within the first order logic of this structure, we can talk about inequalities. If we want to say that a particular term represents a number which is less than or equal to another term, all we need to do is say that there exists a z such that x plus z is equal to y. Again, this requires a quantifier, and we'd like to be able to get rid of that. And we can get rid of all quantifiers that are serving this sort of purpose by simply adding in inequalities into our language. In this language, we can also talk about when a number is even or odd. So we can describe a predicate that determines if a number is divisible by 2, simply if there's some number which, when added to itself, gives us that number. We can also describe other divisibility predicates, such as we can say when a number is divisible by n, if there exists a z which, when added to itself n times, gives us x. It's very common to use the notational shorthand n times z to represent z added to itself n times, but we need to be really careful when we do this. This n here has to represent a concrete natural number, not an element of this structure. And it certainly can't be a term within the logic. We can't have multiplication within the logic of the structure. This has to be some kind of shorthand. The key thing about Presburger arithmetic is that we have specifically decided not to include multiplication within this language in hopes of avoiding the undecidability that we got from Gödel's incompleteness theorem when we studied the natural numbers with addition and multiplication. Again, we should think about this as a concrete number times a term in the language represents that term added to itself n times. Of course, we don't need to add in all of these divisibility predicates. If a number is divisible by 2 and divisible by 3, then it's divisible by 6. But let's throw them all in anyway. So I claim that this is all that we need to add into our language in order to get quantifier elimination. But do we actually need to add these things into our language in order to have quantifier elimination? We wouldn't need to add these if there was already a way of describing when a number was divisible by 2 or divisible by n in the language as a Boolean combination of atomic formulas. As a first-order logical formula, without quantifiers. I won't go through the complete proof of how to do that, but I do want to take a look at what sorts of atomic formulas we have in this structure with the natural numbers and addition, and let's say just 0 and 1, in order to analyze what they can say and give you a sense of how to prove that they can't say things like less than or equal to, and they can't say that a number is divisible by 2 without either involving quantifiers or adding new things into the language. Let's take a look at what sorts of predicates we can describe as zeroth order formulas over this particular structure here. This structure doesn't have any relations to it yet, so the only relation that we have, the only way of building up an atomic formula, is with the default built-in equality relation. And on the left and right-hand sides of this equality, we need to put some sort of term built up out of variables, addition, and our constants. These terms are going to look something like, where we can use additive associativity and commutativity in order to shuffle these terms around so that like pieces are next to each other. It's convenient to use our shorthand in this case. Again, remembering that 3x doesn't actually represent 3 times x, it represents x added to itself 3 times as a formula. This is just shorthand, this is not actually part of our language. It's simply because I'm too lazy to write x added to itself lots and lots of times on the board. Throughout this video, I'm going to want to be able to quickly remind you what terms on this structure look like. So I'm going to call these linear polynomials. I'll describe this as some linear polynomial of x and y. In order to analyze what this means as a predicate on x, y, and z, we're going to want to be able to remove common summands from both sides, so we can cancel out an x and cancel out the 2 y's to just be left with 2x plus 1 is equal to z. And so this predicate has a few important properties. First of all, the value of y doesn't matter. Once we've chosen the values of x and z, either all of the values of y are going to make this equality work, or none of them are. On the other hand, if we've already chosen the values of x and y, then that will actually determine the value of z uniquely. There'll be one value of z that makes this predicate work, and all other values of z will not make it true. And then finally, if we've already determined the values of y and z, well, it's possible that there's an x that makes this work, provided that z is odd, and if not, there isn't going to be an x that makes this work. So sometimes there will be one value of x that makes this work, and other times there will be 0 values of x that make this work. So we know that if we have some atomic formula in this structure, let's say it takes in 3 variables as input, when we determine the values of 2 of the variables, there's either going to be 0, 1, or all values of z are going to make the predicate true. And when we combine these sorts of predicates together using Boolean logic, the resulting predicates, once we determine all but one of the variables, there's either going to be finitely many, potentially 0, but finitely many values of the remaining variable that will make it true, or finitely many values of the remaining variable that will make it false. That is to say, cofinitely, all but finitely, many values of the variable will make it true. And so we can see right away that divisibility by 2 is not one such predicate. Infinitely many numbers are divisible by 2, and infinitely many numbers aren't. And so there's no Boolean combination of atomic formulas that can get us the divisibility by 2 predicate in this particular language. We need quantifiers, or we need to add it directly into our language. And so it can be kind of a fun exercise to work out why exactly we can't say less than or equal to already as a 0th order formula over this structure here. Or why can't we talk about divisibility by 2 if we have 0, 1, and less than or equal to? So I'll let you work those out if you're interested. For now, though, I want to focus on this structure here. We've only added in things that we could already talk about in the first order logic of the natural numbers with addition. But again, we needed quantifiers in order to do that. And so my claim is that this structure here has quantifier elimination. In this structure, we don't need quantifiers in order to be able to express anything we could express in the first order logic of this structure, which is equivalent to the first order logic of this structure. Again, we only need to show that we can get rid of one quantifier, and then we just need to apply that process recursively from the inside of a formula out in order to get rid of all of the quantifiers in that formula. And we only need to show that we can eliminate existential quantifiers because universal quantifiers are just the negation conjugate of the existential quantifier. So suppose that we have some sort of formula with a single existential quantifier saying there exists an x such that something holds of x and then a bunch of other variables are potentially involved, where this formula here has no quantifiers in it. So it's just a Boolean combination of atomic formulas. And again, our goal will be to rewrite this formula as an equivalent formula that doesn't have these quantifiers to it. Let me show you a cheating way in order to get rid of this quantifier. If we were allowed infinite disjunctions, infinite ors, we could simply say that phi held of 0 with the values of y0 through yn being what they are, or phi held for 1, or phi held when x equals 2, or and so on and so forth. This is, of course, equivalent to saying that there exists an x in this structure that satisfies this formula here, but it's not a first-order logical formula. It has an infinite or in it, and we're not allowed to have infinite ors. But otherwise, it is a perfectly valid way of getting rid of this quantifier here. And in fact, if we had a structure that only had finitely many elements to it, this would be a perfectly legitimate way of getting rid of that quantifier. All we would have to do is turn there exists an x such that phi of x, y0 through yn into an or over all of the elements of the structure of phi of that element y0 through yn. But alas, this structure is infinite. We're going to have to narrow down our search of potential candidates to some finite list. But that's exactly the approach that we're going to take. We are going to, by looking at the contents of this formula here, determine a finite set of candidates such that if there's any x that makes this true for any values of y0 through yn, it's going to be one of our candidates. And the candidates are, of course, going to depend on the values of y0 through yn, but in ways that we can describe within the language. And so we'll narrow this down to a finite set of candidates, and that'll allow us to cut off this infinite or, it'll just be a finite or over our finite number of candidates, and that's going to give us our quantifier elimination technique. Admittedly, this is a little bit disappointing, especially if our list of potential candidates is really, really long. Just like before, we're going to want to simplify this formula down a little bit in order to get a handle on what it can look like. First, we're going to want to translate it into disjunctive normal form. That is, an or of a bunch of ands of atomic formulas and their negations. But I'm actually going to want to make a slight change, and this is just for notation's sake. You don't actually have to do this to make the proof work. Everywhere that we have a negated atomic formula, I'd like to turn it into a disjunction of positive atomic formulas. Using these sorts of translations here, everywhere we see a negated inequality, we can turn it into an or of atomic formulas. Anywhere we see a negated divisibility, we can again turn it into an or of positive divisibility atomic formulas. Right? A number is not divisible by 3 if and only if that number plus 1 is divisible by 3, or that number plus 2 is divisible by 3. And again, when I write 2, I really mean 1 plus 1. And of course, if we have negated equality, we can turn that into some inequalities. If we first take this formula here and translate it into disjunctive normal form, and then replace the negated atomic formulas within that formula by their corresponding positive versions, the resulting formula, it's no longer going to be in disjunctive normal form. It's going to have some ors on the inside, but it's not going to have any negations anywhere, which is really handy. And then we can get the formula back into disjunctive normal form by using the distributivity property of ors and ands. As such, we're able to translate this formula here into an equivalent formula that is just an or of a bunch of ands of atomic formulas. In other words, it suffices to show that we can eliminate this quantifier in case this formula here is an or of ands of atomic formulas. Next, we're going to want to do the same trick of pulling the ors out of the existential quantifier. If we have a formula that looks like there exists an x such that something is true, or and so on and so forth, and something is true, where of course these things are just going to be ands of atomic formulas, we can just using logic translate this into the equivalent. There exists an x making the first part true, or there exists an x making the second part true, and so on and so forth. And so all we need to do is have a procedure for eliminating this quantifier here from all of these different formulas, and then we eliminate the quantifier here, the quantifier here, the quantifier here for all of these different pieces, and the resulting formula is going to be a quantifier-free equivalent formula to the original formula. And again, each of these pieces is just going to be an and, a conjunction of atomic formulas. So it suffices to show that we can eliminate this existential quantifier here when this piece here is just a conjunction of a bunch of atomic formulas. Instead of working this out in general, I'd like to work this out for a specific concrete example of phi in hopes of showing you all of the different pieces that you need to put together in order to have the general proof and of course the general algorithm for the quantifier elimination process. If we're looking at a general atomic formula, we might have the same variable showing up on the left and right-hand side of the inequality, but again, we can just get rid of those by subtracting corresponding terms from both sides until one of the sides doesn't have that variable in it anymore. Again, I've used the shorthand notation that I introduced simply to avoid having to write x added to itself 5 times. So here's the formula that we'd like to eliminate this existential quantifier on x from. Specifically, we'd like to be able to write out as some sort of Boolean combination of atomic formulas involving just y and z, some sort of condition that determines whether or not there exists an x making all of this true. And again, our goal is going to be to narrow down, to somehow extract from this a finite list of candidates for values of x, where if none of the candidates is a working value of x, then there are no values of x that make this true. And so we can say that this is true if and only if an or over all of the possible candidates of this bit here is true, which will be a long but finite Boolean combination of atomic formulas involving just y and z. Our first step is going to be to multiply everything through in order to get a term involving x that's a common multiple. If we multiply both sides of this inequality by 15, we get an equivalent inequality that has a common term of 30x. We'd also like to be able to multiply this term here by 10 in order to get our common 30x term. And in order to do that, well, saying that something is divisible by 2 is equivalent to saying that 10 times that thing is divisible by 20. Our next transformation that we're going to want to apply is going from saying there exists an x such that 30x satisfies all of these things to saying that there exists an x which is divisible by 30 that satisfies all of these things when we replace 30x by just x. So all in all, we were able to take our original formula and translate it into an equivalent version that doesn't have any multiples of x in it. So let's try to concretely understand what this formula is trying to tell us. These inequalities here give us upper and lower bounds on x. It gives us an interval in which x must fall. And these divisibility requirements are requiring that the remainder when x is divided by 20, 18, and 30 are specific values, depending on whatever y is and whatever z winds up being. This inequality here gives us a lower bound. I guess if we want to include the lower bound, we have to add in a +1. That's fine. But we know that x has to be at least 12z plus 24 minus 6y plus 1 from this inequality here. Of course, we didn't have subtraction in our language, but let's not worry about that yet. These two inequalities actually give us two upper bounds. And again, I'm just subtracting one because these are strict inequalities. So the range that we're going to want to look in is between this value here and the minimum of whichever these two values are. Of course, if these values are less than this value here, then there aren't going to be any solutions. And so we could, if we wanted to, remember that our goal is to translate this into an equivalent Boolean combination just involving y and z. If we wanted to, we could throw in as kind of like a first check this to make sure that both of these are in fact greater than this value here in order to get any solutions. So we've narrowed down the potential candidates that we want to look at, potential values of x that could make this true, down to some list here. The problem is that this list isn't something that we can just OR a bunch of concrete numbers together in order to get a concrete formula. Because this list here depends on the value of z and y. Specifically, the length of the list depends on the value of z and y. And so we'd be ORing together a number of things that depended on the value of the variables in the formula. That's not something that we can do in first-order logic. We need to reduce this list of potential candidates down to something with concrete finite length. So again, we're looking for some value of x within this range here that has these specified remainders when we divide. That x is congruent to -6z modulo 18 and congruent to -20y minus 10 modulo 20 and congruent to 0 modulo 30. So we have specified remainders, and the Chinese remainder theorem says that if there is a value that has these desired remainders, and there might not be, it's possible to have contradictory requirements. I don't know if this specific set of divisibility requirements gives us anything contradictory, but it's certainly possible that we can have contradictory divisibility requirements, like saying that a number is odd and divisible by 10. But if there is an x that makes this work, then in any consecutive 180 numbers, there will be an instance of an x that makes this work. Because within every group of consecutive 180 numbers, all combinations of remainders modulo 20, 18, and 30 that are compatible with each other will show up. And so all we need to do, actually, is look within the first 180 numbers on this chart here. Now, of course, this might not be to scale. It might be the case that these upper bounds are somewhere within here, within the first 180 terms, and that's perfectly fine. Those x's will clearly not be the candidate that we're looking for if they're larger than this, because we're also going to check to see if they satisfy these inequalities. We're checking to determine if x satisfies all of these here. But if there is a value of x anywhere in this interval that makes this work, there's going to be an x within this first 180 terms. And so if we call this bit here phi of x, y, z, we're just going to want to check to see if there exists, for some j between 1 and 180, a value that makes phi of 12z plus 24 minus 6y plus j, y, z, true. And so this is it. This is almost it. This is almost a concrete formula, right? It's just the OR of 180 different things together. It's a really long formula, but it is a concrete formula. It's just an OR of 180 different things. The problem is it involves a minus sign, right? We're plugging in this term here for all of these x's, and there's a minus sign here. And I didn't give you a minus sign, and I did that specifically because the natural numbers aren't closed under subtraction. So how can we deal with that, right? When we're trying to translate this into a formula that's actually in our logic, how can we deal with plugging this in for this x here? And let's say that j is some concrete number like 7, just to make this a little bit more concrete. This will be one of the terms that we're ORing together within here when j is equal to 7. And of course, this is not a term in our language because it has subtraction. But we can turn this into a formula within our language by simply taking this minus 6y and moving it over to the other side of the inequality. And of course, we can cancel the y's if we want, but we don't have to. We're just looking for a formula within our logic. And similarly, we can do the same for all of these other inequalities here to get rid of that minus sign coming from this minus 6y. Then if we want to translate a divisibility requirement with a negative 6y in it, again, we'll assume j is equal to 7 just to give this some concreteness. We can just translate this into a formula where the negative 6y is replaced by positive 9y, because that'll preserve divisibility by 18. And so again, we were able to translate our formula, which wasn't in our language, into an equivalent formula that was in our language. And we can do that same translation here. We do need to be a little bit careful if this lower bound is less than 0, which we can do by checking an inequality between 6y and 12z plus 24. If this thing is less than 0, we want to start our count not from this lower bound, but actually from 0. And that would actually be easier. We would just check something like that. And so we need to have a special case that says if 6y is larger than 12z plus 24, we actually look at this OR of a bunch of formulas together. But that's fine. That's just Boolean logic. And again, when we're checking these potential candidate values of x, we are checking to make sure that they satisfy the inequalities and the divisibility requirements to make sure that this actually does work, that x really is the x that exists here. So hopefully that gives you a sense of what the general proof looks like. I haven't handled the case where there's an equality here, but it's actually easier to handle cases where there's equalities here. And I also haven't handled the case where there's no lower bound. If there's no lower bound, if none of the inequalities present give us a lower bound, then again, we just start our search from 0. And if there are multiple inequalities that give us a lower bound, we start our search from both lower bounds. So if we had 2 lower bounds in this case, we'd actually be doing 3 times 180 different searches. One search from this lower bound, one search from the other lower bound that we got from the other inequality, and one search from 0 in case these lower bounds were actually less than 0. So again, it's going to be a really long formula, but it will be a 0th order logical formula, and that's what we're looking for. Again, it's a concrete algorithm. You could actually write a computer program that carried out this translation. And if you had a formula that had lots of quantifiers in it, you could carry out this sort of transformation step by step, eliminating quantifiers one by one until you got an equivalent formula that didn't have any quantifiers in it. However, this is a terribly inefficient process. The size of the formulas that we wind up getting when we do our translations are huge. And so the actual process is also going to take a long time if we want to do several transformations, if we want to eliminate several quantifiers. Just like in the case of the real numbers, there are lots of practical applications for having a way of deciding whether a formula in this logic is true or false. And so there's a great deal of research out there trying to optimize this quantifier elimination algorithm in order to get a better algorithm for deciding whether or not certain formulas are true or false. If we had a formula in the first order logic of Presburger arithmetic that didn't have any free variables, so it was either true or false, and we wanted to determine if it was true or false, we could, well, the formula is already a formula in our expanded version of Presburger arithmetic that had quantifier elimination. So we just take our formula, apply the quantifier elimination algorithm to it, to get an equivalent formula that had no free variables and also had no quantifiers, so had no bound variables. In other words, it would be some Boolean combination of inequalities and divisibility checks on concrete numbers, one added to itself some number of times, or maybe 0. And then we would just have to work out whether or not that Boolean combination was true or false, which is a straightforward thing to do, and that would tell us whether our original formula was true or false. Quantifier elimination also gives us a really good sense of what sorts of things we can express in the first order logic of our original language. Anything that we can express here has to be some sort of Boolean combination of equalities, inequalities, and divisibility requirements. But we can actually do this a little bit better. In the next video, I'd like to show you another approach to trying to understand the expressivity of this particular logic. Quantifier elimination also gives us another advantage. If we're willing to look at our quantifier elimination procedure very carefully, we can actually extract from it an axiomatization of our structure. Suppose that we have a true first-order logical sentence within this structure. We can then apply our quantifier elimination technique step by step to reduce this down to an equivalent quantifier-free formula. So if we want to prove this original formula, all we need to do is prove that each formula in this chain is equivalent to the previous formula in it, provably from our axioms. And finally, we need to prove this formula down at the bottom is, again, a quantifier-free, free variable-free formula. So it's just going to be some sort of Boolean combination of inequalities and divisibility requirements of concrete numbers, just one added to itself some number of times. And so we just have to make sure that our axioms suffice to be able to actually prove all of those things. Assuming, of course, that they're true, which is assuming that our original formula is true. And so by asking, what axioms do we actually need in order to prove these basic formulas? And what axioms do we need in order for these steps? What axioms did we actually use? What properties of the natural numbers with addition did we actually use in our quantifier elimination procedure? If we do this very carefully and remove a bunch of redundant axioms, we have to think about, okay, what sorts of things are implied by what sorts of things? And of course, if we're just trying to axiomatize within this structure, we don't want to talk about the properties of inequalities or divisibility. We want these to kind of emerge as based on how we define inequalities and divisibility. But this will give us our complete axiomatization, yet another useful thing that we got out of this quantifier elimination construction. And in fact, even better than that, because we have an algorithm that does this translation, we actually can produce an algorithm that provides a proof of any formula that's true within this first order logic. This step-by-step process of showing a particular axiomatization will show up again when we talk about weak S1s, but in a slightly modified way. So let me know if you have any questions or comments in the comment section down below, and I hope to see you in a future video.